Great, thank you everyone, and a big thank you to KX for having us here and being great partners. I am the introduction notwithstanding, I'm not a language bigot. I do a lot of my work in Python, but actually my job is to be the CTO of Anaconda, and I'm the co-founder there. And one of the great, I think one of the great strengths of the Python ecosystem is that it is polyglot, and it has been a very big tent for a long time. And that's in fact one of the reasons why I think it has the popularity that it does. We don't really, I guess we have some language purists, but I don't hang out with those people a lot. I tend to be much more of a big tent kind of guy. So today I'm going to talk about my 20-year journey with Python, the things I've learned, the things I've seen, and sort of my personal journey as a software dev. And hopefully this is interesting to most of you here in the room. Of course, talking about oneself is most interesting to oneself, but I think there are some generalized lessons we can learn about technology, about the evolving and changing nature of languages and all that. And so for those who are not aware or who are not familiar, Anaconda is the most popular Python data science platform. So we include a lot of packages, a lot of libraries. We make some of the libraries and do some of the cutting edge work at the vanguard of Python for data analysis, numerical computing, et cetera. We have over 2 million downloads per month. And that's of the main installer itself. The packages go to the tens of millions of downloads per month from our CDN repositories. And our Anaconda platform, essentially, the distribution and the related repositories, those are parts of many commercial offerings. We also have an enterprise offering that some people are aware of. Unfortunately, many people are not aware of it, and we're trying to rectify that. But our enterprise platform really helps the businesses and enterprises that have a lot of Anaconda free users operate and be effective in an enterprise environment, which oftentimes is locked down, has various compliance and governance controls. And oftentimes, we hear from customers or from folks at large enterprises that their data scientists will go home and be more productive in the evenings and on the weekends because they are in their home network and they can grab all the code they need to actually do some of the dev they need to do. So the enterprise platform helps people bridge that gap and helps IT get a sense of what the people are doing with all their crazy notebooks and their crazy Python scripts, and then all the people doing the notebooks and crazy Python scripts can get all the stuff they need to, and everyone's happy. So with that, if you want to know more about that, if you want to know more about our integration with KX and KDB, please talk to Francesca, myself, Michael. We have a table out there. So happy to talk about all that stuff. So today I'm going to talk about sort of the life's big questions, at least as it pertains to software development, because my life as a coder, I feel like constantly revolves around these questions. One of them is, what is the nature of a programming language? And then if we think we have an answer to that, then the even bigger question, what is the nature of software itself? And these are important questions to ask today. In this time, a lot of things about this are changing. And then if you have done, how many people here would consider themselves to be in the field of software, have done software for a while? Show of hands, right. So if you've done any software at all, the general thing you do in software is you're hoisted by your own petard, right? So are we always doomed to be hamstrung by this complexity that we create in the course of just doing our jobs? So I do most of my work in Python. I've been doing Python for quite some time. But Python is a language. I've watched it evolve and grow. It also has these existential questions to face. Python, I think this is from the Wikipedia entry on it, Python did not have ambitions to be like a very, very popular, massive mainstream language. It was trying to be a teaching language. It was trying to be accessible. It was going to basically consider a job well done is I've displaced Bash, right? So in this desire to create an accessible and teachable language, we've come to create a really interesting and powerful ecosystem. And so it's always suffered criticisms about performance and scale because it was meant to be a replacement for Bash. So there's other questions of scale too, which is around, from the more seasoned software developers, the question of scaling of teams and scaling of code bases, right? So the question, then for languages is what actually is performance, right? What do we really mean when we talk about performance? And what is scale, right? Like I alluded to, there's questions of scale of the code base, scalability and maintainability of that, as well as scale of the teams and the people around the code, and there's scaling of the actual compute, infrastructure itself. And then another question, at least for Python world, is this distinction between scripts and software. And we see this in data science and in numerical analysis a lot too. A lot of us write one-off scripts. But then sometimes those scripts then really need to become software. And what is the gap? What's the delta there? So in the Python world in particular, these questions come up. Now, I only have 20 minutes, so I'm not going to be able to answer these questions for you, but I will tell sketches and maybe paint some vignettes of ideas that might inform the folks here in this room. I have 25 minutes. Okay, well now we will be able to talk about these topics actually with that. So really just a little bit of background. I am actually not what they call a classically trained computer scientist. I'm actually a physicist. How many people here are physicists or see? Okay, in New York you hit a lot of those in finance. So anyway, my early years actually were spent doing all manner of just coding, playing around, basic and Pascal and all that stuff. Some Hypercard, which was fun. My first job out of college was actually to do this very, very intensive, high-performance computer graphics simulation. And it was a combination of math and statistics and debugging Visual Studio 6 template handling. But I really, really got bought into this culture of performance, 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 right? So raw computational speed. I sat next to a guy who was a hardware engineer. He really, he was looking at disassembly more than he was looking at C++. So, but in the process of doing that, I also got to rub shoulders with people who were trained computer scientists, and they were talking about things like meta classes and continuations, and I didn't really know what these things were. But I started sort of at least hanging out with people who talked about these kinds of things. And so by the time that I was done with that startup as it folded, I went to Austin and I entered what I would consider my journeyman phase, where I did a lot of, I at that point I think had somehow earned the right to call myself a software engineer, and I would go around doing consulting as a software engineer. And I basically focused exclusively on doing scientific computing consulting in Python. And that was on paper it was only 6 years, but it seemed like a lifetime actually. And I primarily used Python. I was exploring using other languages, built integrations to various things, but it was using Python and Python's extensibility that I was able to explore different other paradigms beyond the C++ and the Algol style paradigm. And I did functional programming, metaprogramming, did a lot of maybe too much metaprogramming. And I was able to generalize my learnings from the field, from the numerical simulations in computer graphics into numerous other fields. So it was a really fantastic experience. That was also the time I started participating in the open source community. I went to my first PyCon in 2005, my first SciPy as well, really started rubbing shoulders with people. I have a small footnote of credit in launching what ultimately became the Jupyter Notebook, one by asking a really annoying question, and two by providing a little bit of funding to the initial notebook efforts around IPython. But it was in the process of writing, doing consulting, you do a lot of projects, and you start seeing patterns between these, and you start finding yourself solving the same problems over and over. And my sort of internal development around coding really at this point started to hinge around the question of expressiveness and correctness. And so I sort of ended that period with a pile of consulting in HFT and finance and investment banks here in New York. And I really came to a point where I was like, I need some time to think about what exactly all this is about. I sort of got a sense, a smell of some deeper logic behind, and maybe some deeper patterns behind how we write code. So I took a sabbatical year, which is sort of a weird thing to do. It's self-funded sabbatical. Also, I had my wife and I had our first child, and he wasn't sleeping, so this actually worked out pretty well. But I wanted to explore interactive visualization. I wanted to bring D3 to Python, but on very large finance scale data sets and scientific scale data sets. And so that led me, pulling that little thread, led me down just a rabbit hole of various things. You see Alice, and she has a little bottle of Drink Me, and everything basically goes downhill from there. But I did a lot of reading. I did a lot of thinking about this stuff. And it was actually not quite so much the little bottle there. It was more like the drinking from the fire hose. It's a great movie. And so I was looking at a lot of, by the time I started thinking about really doing scalable computing, really doing parallelization, SIMD and scale out and all these things, I started basically looking at all this vector processing research from the 60s. And there were some new things as well, like the DARPA projects on high productivity languages. But at the same time, if you think about 2011, big data was really starting to blow up. So everyone was talking about big data. And the Python ecosystem had just gained pandas as a data frame tabular structure. And we were discussing what is the future of performant Python as well. So we ultimately realized, okay, we have to have a bigger conversation on how we move code to data. And not just move code to data, but move the right code, and that is to move the right ideas to data. And one of the things I uncovered, maybe the Mad Hatter or maybe whatever, the Red Queen, while I was in my sabbatical, was I found what I would consider my red pill into the world of real computing, and that was when I discovered Forth and the world of concatenated languages. Right. And so I decided to just kind of nerd out on that a little bit, right? And what I realized was, okay, if every call is call CC, right, the world changes. If concatenation is fusion, because one of the hardest things about trying to do something like performant D3 in Python is loop fusion, right? When you have these imperative languages, loop fusion. And so when you realize fusion is just string concatenation, like that's a mind-blowing concept. And ultimately what it got me to realize was that all of the things that I thought were hard problems, all the things I kept running into as a consultant or even as a C++ programmer, doing Python, doing C++, all these different things, they're all constructs, right? These are so many of the barriers, so many of the limitations we run into, they are constructs created by the way we have decided to chop up the world of runtimes and interpreters and all these things. And actually, if you go to concatenative language, you have this great unity from parser down to runtime. It's just absolutely elegant and beautiful, and dispatches whatever the heck you want it to be, which is really something else. So, so after I did this for a little while, and this is bad for physicists to do because physicists are already very conceited people. They believe they understand the underlying structure of the universe, so every problem is basically bookkeeping, right? So once you do something like fourth or concatenative language, you take that physicist conceit and apply it to computing, and now you think you understand everything. So I was no longer scared of the people talking about Haskell and monads. I was no longer, weird things like fried quotations and factor were easy to understand. So a lot of these things all came together for me when I started really exploring concatenative languages. And it seems to me quite a shame that, well, to be clear, this is not my first concatenative language because technically RPN on my HP48 was my first concatenative language. But in any case, stack-based concatenative languages like this are, I think it's a really deeply powerful way of looking at the world, and it's a shame that it's not more broadly known. But this is something that I sought to try to fix a little bit, and I started my own company actually called Continuum Analytics at the time, now Anaconda. And if you look to 2011, there's a video of me at SciPy 2011 presenting to a room full of Python people, and this is all the names you might recognize if you're a Python user, people like Wes McKinney, the author of Pandas, John Hunter, the creator of Matplotlib, Brian Fernando, creator of IPython, Travis, my soon-to-be co-founder, all these different people. I was talking to them about Forth, and I was explaining to them about this amazing stuff and all this stuff. So I started the company because I wanted to pursue how we make Python better by taking some of these ideas into it. And I realized by going down to that level where every call is call CC, where dispatch is whatever you want, at that level I realized there is this iron triangle, almost like a CAP theorem for languages, between expressiveness and correctness and performance. And every language basically takes some projection onto that triangle, those three axes. And you can look at it that way, but if you overlay on top of it, maybe something more accessible, the idea of this distinction, basically all computing to me, it seemed like, could be split into this trinary or this holy trinity of three concepts. One of them is expressions, one of them is data, and one of them is compute. And all languages, all technologies we have, basically, usually they reject or throw out one of these three and just merge two of them together to make this a little more concrete for people. This is kind of what I'm talking about when I talk about these things. So the project at Continuum, now Anaconda, was can we build some technologies, can we build some tooling for Python, can we maybe move Python forward to a different restricted subset of Python that could actually solve this problem in a more holistic way, that could bring data and expressions and compute together without, and work on them all in a first-class manner. If you look at what was available at the time, every single one of the primary tools that one might use to tackle that suffered from one or two categories. And so with that lens, so many of the computing problems that we saw at our customers or in the world in general, they really could break down into a lack of synthesis of these three, a lack of balance between these three fundamental axes. Now, the good news is, of course, since that time, a lot of new things have come along. A lot of great work has been done in the Python ecosystem. We have now technologies to lower Python down. We have technologies and we have libraries that have raised things up to certain levels. And things are starting to converge, so I feel good about that. But I think that we're still a little ways out. I think we still have a bit of work to do. And so, in my day-to-day life now, I'm still working on trying to untangle this holy trinity. Not untangle it, but to, again, emerge some concepts, first-class concepts around each of these three things. But to go into that, we can talk about it at the cocktail hour. We can, it could be a 3-day symposium if you want to do that. I can talk about that stuff for a long time. But what I'll talk about now is the lessons I've learned in this progression. And one of the things that I've learned that's very, very important, I think, it's quite actually universal, is that code is actually culture. Now, as coders, we tend to think of code as artifact. It's sort of a byproduct of what we get paid to do. And what I've seen actually in watching the evolution of the Python ecosystem, the SciPy ecosystem, is that software is more than just tech. It is a language, and as a language, it is a cultural activity. It's a cultural artifact and phenomenon. And it creates communities, and those communities actually form the cultural activity that is the development of software in that particular language. And a few years ago, there was a really famous Rubyist who fled the Ruby community to join the Python community. And he brought his particular firebrand, and some of you may know who I'm talking about, but he left the Ruby community in a particular interesting way. He wrote a series of blog posts basically flipping the bird to everybody in the Ruby community. He joined the Python community and sort of announced, here I am. Aren't you all proud that I'm here? And then proceeded to not really get a lot of people interested in kind of that firebrand energy he brought. Now, he did some really great work after that, and people really like his work. But the point is that these different communities have vastly different kinds of values and what's accepted behavior and norms. So Lawrence Lessig, years ago, had this really pithy quote that code is law. And of course, as a lawyer, he would say that. But what I've seen is really that coding as an activity is absolutely cultural. So that's one of the primary lessons, that we tend to sort of make software this very inorganic kind of technological activity, but actually the practice of coding and development and software development is a cultural activity, and software is a cultural artifact. Second is that we are quickly hurtling into an era of data literacy and computational literacy. So every single field, every single major kind of activity of human civilization is going to be impacted by the ability to think quantitatively and to do so on the basis of some compute framework or some computational infrastructure. So data exploration, exploratory data analysis in the style of John Tukey is now absolutely the thing that everyone has to do. The odd thing is that for 20, 30 years, we've gone by with just reporting, basically. Like the people in this room, maybe the people that report to the people in this room, there are some people who do actual predictive analytics and quantitative analysis, certainly in finance here in Manhattan, but most of the rest of the world gets by on Excel reports and Crystal reports. And so that's a really interesting thing. That's opportunity for all of us, but at the same time, it is also culturally challenging because most businesses are not oriented to think in that kind of data-driven way. So, but anyway, to this point about this era of data literacy, we are going to have to all be able to talk about how we did our analysis. We're all going to have to be able to have shared beliefs and shared values when it comes to what is a truly reproducible result, right? What is actually producing an artifact that people can do what-if analysis on. All these kinds of things are, again, cultural questions, questions that are going to come right screaming to the forefront as we start deploying machine learning at scale across the world. So the thing that I would drive home here is that a language, a computer language that isn't just there to do some CRUD in a database, but a computer language that helps someone actually do analysis on data is thoughtware. And in that way, it is essentially a derivative, or it's an additional bolt-on to the English language or to whatever native human language you speak. And so when you talk to other people, you're going to have to explain those ideas to them as well. So that's something that's actually, it's really become obvious to me in the last several years as I watched Python get into various organizations and seen the cultural gaps between what the organizations are able to speak from a technology perspective and what the Python advocates are able to speak. And sort of maybe one last point is that we are rapidly advancing, sort of tied to the previous one, we're rapidly advancing into a post-PC era. We're already there for the most part. But the collapse of the Windows Intel monoculture has actually left this gigantic vacuum. And so many things are being built and thrown into that pit. We call it a Cambrian explosion, we call it a pit, whatever, a cesspool, whatever you want to call it. But essentially there is a tremendous amount of innovation, there's also a tremendous amount of band-aids and as-if innovation going on. A lot of blurred lines between what used to be clear strata of a separation of concerns of technology and of IT organizations. All these things are all merging together now. And it's interesting, right, because you have people with titles of senior engineer, senior whatever, analyst. You have people who have these senior titles that have only lived in the Wintel monoculture, really, professionally. And so to actually think down to bare metal, I mean, Rowhammer, Spectre, these are great ways for them to wake up, right? But to think down to bare metal, to think about scale, not only as just something you buy as a component from whatever vendor you've got, but actually think about scaling infrastructure to meet the needs of a problem is something that actually I think most IT and dev organizations haven't had to do in a while. And I don't mean that to be, I don't want to be too flippant, but I mean to meet the needs of quantitative analytical problems, the kinds of problems that people in this room want to solve. That is something that's very, very difficult for most organizations. They tend to put people in the sandbox or in an ivory tower, give you lots of big iron, and you do your thing, right? But to actually say, we have to production deploy this big thing now, that's really weird for people. So, and where we're moving to here really is we're going to, I think people, especially with the Hadoop sort of hype cycle and everything, a lot of people like to think that they're doing big data. A lot of people want to think we're doing data-centric computing and all this stuff. What they're really doing is just SQL on slightly less robust software, right? But is this being recorded? No, actually, so Hadoop works great for many use cases. So, but they're laughing, I'm not. I'm serious, Hadoop works great for many use cases. But the point is that the vast majority of what people are doing with Hadoop is it's schema on demand, and a schema after the fact, but they're hitting it with SQL. All right, so if SQL is good enough for you, then that's great. But the key point I want to make here, actually on the slide, is that we're moving from what people like to think of as data-centric, we're moving from that to data-led. And there's a big difference, because data-led means you have to be able to do modeling, simulation, exploration on those kinds of data sets. And so I think that in the next few years, as the slide says, 4 to 5 years maybe, we're going to see a wholesale shift away from the 1980s style of thinking about what computing is. And we're going to actually be thinking about inference engines. We're going to think about wholesale live prediction engines as being the joint artifact of both the IT teams and the software dev teams and the modeling and analysis teams. Everyone working together to build a unified artifact as opposed to everyone contributing a piece and hoping it all sort of like hangs together. And so I think what we're going to do is we're going to stop talking about computing in general terms, and this is my hope at least, we'll focus more on talking about what computing actually enables. And my prediction is that in 10 years' time from now, we're going to be, most of the code that anyone writes will be tied into these living, evolving inference engines. That's just what the world is going to be. Very, very few people are going to be able to write apps that just sit there and just do one thing, pull out of this database, update that database. We're going to be kind of done with that. So as technologists, we have to ponder that. If you buy that, if you believe that, if you think I'm mostly correct but off on time, whatever it might be, in the world where we're building inference engines, in the world where analytical reasoning is facilitated by massive compute engines, and that same thing has to be replicated in fidelity in production, in that kind of world, what is the role of devs and of quantitative reasoners like us, right? And if we, I think, if we just focus on the problem spaces that we're comfortable with inhabiting, if I just sit here and encourage more people to write more Python libraries and don't think about the bigger question, we run the risk of being relegated to just infrastructure. And so if we want to have an impact on that world, if we think we have interesting things to do and say in that world, we have to look up. We have to be looking forward at this kind of future and really think about what kinds of culture, what kinds of use cases our code and our libraries are actually enabling. Thank you.